actually my first talk in person since the beginning of of the COVID, so I'm super excited to be here. I'm going to talk about some work. So it's a combination of a survey I've been working on with Mike Hewitt, some work with my students Greta Lage, Robin Legault, and my colleagues Andrea Lodi, Guillaume Rabusseau, and Gilles Savard. So it's sort of a mix of what I've been doing as a scientific advisor working for a company and some of the academic research and sort of where we see this going in the future. And it relates really to the challenges, so thanks for the introduction, about when you're kind of looking at this as a system perspective, where you have users of transportation and mobility, and when you want to optimize those systems. So I'm going to focus a lot of demand, but actually you can think about other kind of prediction problems. But we really, when we're looking at transportation and mobility, we're really interested in predicting demand. So here you have a few examples. It can be sort of demand for park and ride facilities. I think Eric mentioned that already. We can also talk about freight transportation. So here you're seeing containers, so sort of understanding container movements, or passenger demand for air travel. And then particularly interested in like which seat people are interested or which flights. And essentially it boils down to when, where, and how much of demand we will have. And these prediction tags are quite difficult, and in particular because they're all driven by human behavior at the end of the day, and human behavior can be hard to understand, and people have different preferences, different constraints, and so forth. So typically it's quite hard to accurately predict demand. Now, for transport and mobility, unlike there are other applications where predictions alone are of value, but for transportation and mobility, oftentimes predictions alone are not really of value. They are of value to solve some other kind of problem. And here I'm going to focus on decision-making problems. So when we're looking at the park, like the demand for park and ride facilities, problems that we're typically interested in is understanding how much that demand will be such that we can kind of decide on which are the best locations to look at these facilities, or like what should be their capacity. When it comes to containers, it can be, so we want to kind of optimize the transport services, right? So containers, unlike people, we can move, you know, just as long as they get to the destination at the time they're supposed to be there, we have some flexibility. So then we can try to optimize how these services, would you mind closing the door maybe just, or some, thank you. I was having that in my ear. Yeah, so optimizing the services for kind of transporting containers. Thank you very much. And when it comes to airlines, they're oftentimes interested in maximizing revenue, right? So you want to understand what is the demand for different types of seats and flights and so forth, such that you can price those adequately and maximize revenue. So ultimately, what we're interested in is making these predictions such that we can actually, at the end of the day, solve some decision-making problem or solving some optimization problem. And here I'm distinguishing kind of two important aspects that we're interested related to transportation and mobility. On the one hand, supply optimization. So anything that relates to, you know, what Eric and Francisco were mentioning earlier, kind of planning, infrastructure, transport services, you know, which flights should we operate, which trains should we operate, and so forth. And then you have demand management, which is essentially, given that we have all those services, how do we now manage demand such that we're making better use of the capacity that we planned for? And that we can do through pricing, for example. And so I want to give kind of my view of, and it sort of relates to what are the technical challenges, or kind of like the challenges from a machine learning and optimization point of view when we're tackling these problems. And so on the upper left part, you have kind of these predictions and optimizations working together. So you would have prediction here. I'm going to talk about a prediction as being y, so denoted by y. Here's some function of features x and parameters theta, so you can think about it as a supervised learning problem. And then you have your optimization problem. And so here it's just a very general form. It's written as a deterministic problem, but actually can be stochastic. So essentially we have some objective. Here I denoted by G. We want to minimize it or maximize it, you can choose. And we have some constraints pertaining to our decisions that we're interested. Decisions are Z. They are in some space capital Z. And what you can see here, if you're not familiar with optimization, it doesn't really matter. What you need to really pay attention to is that these Ys, the prediction, they occur in the optimization problem, right? So I'm having this optimization problem, it depends on my predictions. Now, in transportation and mobility, at least the applications I'm familiar with, even the solutions, so I said the predictions are rarely useful on their own. We're using them to make some sort of decision. So we're optimizing these decisions to get better values for our decision variable Z. Now, that gives me a solution, but usually we don't use that solution as such. They go through a human in the loop. So you have some decision maker, some expert, like let's say you're planning, you know, here SBB is organizing this session together, right? So let's talk about trains, right? So you're planning sort of which trains that should run. You would not have necessarily an automatic process, right? You would have some scheduling problem, and then some humans will look at these and say, oh, maybe I will adjust this, or I will adjust that. So they will look at the solution, maybe adjust it a bit, and then they will implement it. So that's kind of the execution phase. And once you implement it, then you're interacting with the environment. So then you will see, how do the people actually behave? Which services do they actually use? And so that's kind of like when they're interacting with the environment, and then you generate new data. So what these problems have in common is that typically they have a human in the loop. That's not specific to all applications in which we're working on with machine learning. They are recurrent. Most of them occur over time, and we sort of solve problems, similar problems, yet with some different twist over time. They occur in a very complex environment, so there is a lot of stochasticity, a lot of uncertainty in this environment. So typically our predictions are not that good, and when we have this interaction with the environment, something new happens, or like COVID happens and ports get congested, and you know, there are all these kinds of intrinsic uncertainties in this environment. And we have this new generation of data. So this is kind of to get you excited about transportation and mobility problems, because these are really interesting. And moreover, somebody who works on reinforcement learning, they can think, okay, so this looks really like a reinforcement learning kind of loop, right? Or if you're working in optimal control. Now, what is specific to these, and let me see if I can use my mouse here. Yeah, so this optimization problem here typically pertains to a network where our feasible space here, Z, which is essentially all the constraints you may think of. So if you have a scheduling problem, you will have like these category of people, they don't like working weekends. These ones should work weekdays. They have kids, so they cannot work later than 4, and so forth, right? So think about all the constraints you want to put on your problem here in our feasible set Z. And these are typically highly constrained problems, and we want to make sure that our solution satisfies all of these constraints. So these problems are not always a good fit for reinforcement learning because of all of these constraints, and typically they are network constraints. So these we're often solving with mathematical programming. So they're often discrete optimization problems, sometimes combinatorial optimization problems, which are intrinsically hard to solve. So when we're looking at machine learning in this context, I'm dividing sort of like algorithms or solving methods and models. So when there's been, a search in the literature on solving methods, in particular over, say, the last 5 years or so. So either looking at somehow speeding up the solution. So if I'm going back, like really speeding up the solution of this problem, whether you have predictions inside or not. And so there are essentially 2 categories, either trying to augment solution methods already developed for combinatorial optimization models with machine learning. So if you're familiar with branch and bound or like ways to solve discrete optimization problems, you can think about heuristics. Those are driven to a lot of extent of heuristics, like on which variables would you branch, so you're doing a tree search, and so you can sort of augment these methods with machine learning. So there's been a lot of research on that. There's also been a lot of research like trying to predict solutions completely bypassing these classical solution methods for combinatorial optimization models. So learning sort of like end-to-end this solution, just giving machine learning the features describing the problem instance, and then the machine learning algorithm is supposed to spit up just the solution, right? So no other solver involved. And there is some great surveys on that topic. I'm not going to focus on the solving method so much today. I'm going to talk about what I say models here. And you can see that these squares intersect somehow, because obviously when we're changing models, we also need to work on the solution methods. But I'm more going to talk about this integration between prediction and optimization models and why it becomes very challenging to solve and how you can deal with it in practice. Okay, so the talk is essentially split into 3 parts. So I'm going to start with the core, which is really like this integration of prediction and optimization. And I'm going to give an example of some work I've been involved in, how that can be done. Then I'm going to say, okay, so these prediction problems, actually they become quite hard, and you need to take into account specific aspects when you want to use prediction for optimization. So I'm going to talk about decision awareness in learning and why it is important and why it can be of high value and why it's a super exciting topic to work on. And then I'm going to finally talk about measuring impact. So, you know, this figure that I had earlier, and you're kind of implementing solution in practice, how do you actually assess how good you are? And I'm going to talk about why that might not be as easy as it sounds. Okay, so one can think like this, maybe it sounds obvious, like why aren't we just, integrating prediction and optimization? And the thing is that these literatures and also in applications in practice are often kind of evolving separately, right? We're doing some really fancy stuff on the prediction side, but we can't really use that for the optimization because they don't play well together. And so when we're working on solving combinatorial optimization problems, often we just assume that demand is fixed and known. But demand is never fixed or known, right? We have this intrinsic uncertainty related to demand, which makes it not necessarily perfectly known. Even if you have predictions, often you have a fairly large error associated with them. So it's not known. And it's not fixed in the sense that demand will vary depending on the decisions that we make. So if I change the price for a certain transport service, I expect my demand to change as well. I don't expect demand to be indifferent to the price I fix, right? So these are really interplaying together, but a large chunk of the literature on combinatorial optimization problems just assume that demand is fixed and known. Okay, so if we don't do that, what happens? So here I try to illustrate. So essentially we're having the same sort of notation as before for our optimization problems, and now I'm having my predictions. But you think about the features of my prediction model now suddenly become some features that are exogenous, right? So they do not depend on my decisions, but then you have your decisions in there, right? So you're starting to have this interplay where I'm making predictions, but as I'm changing, so if I'm solving this optimization problem, I'm searching over the solution space, and as I'm searching over my solution space, I need new predictions, right? Because this here will also depend on my decision variables. Now, this becomes a very challenging problem to solve, and essentially what we'll categorize it is that it's optimization with endogenous demand or endogenous uncertainty, okay? Because it's endogenous to my optimization model. And there is surprisingly little literature on this. So if you're a PhD student and you want to have a super exciting, quite difficult topic to work on, this is a good one. Okay, so there is work in stochastic programming where kind of decisions impact probability distributions or uncertain model parameters. There is some work. There's some work in robust optimization where we will call it decision-dependent uncertainty sets. And then there is a chunk of literature that I'm going to dwell down to a little bit more, which is optimization with random utility maximizing users. So random utility maximization models is something that economists have been working on quite some time, but they're also kind of related to some of the machine learning models that we see. And actually this is a way to kind of bridge the gap between the two, so literature on kind of predicting demand and doing optimization. Okay, so where these problems occur is often so in bi-level programming. So you can think of Stackelberg games, or when you would have sort of like a hierarchical decision problem. So you would essentially, now I flip these so you can see there is one on top and one on the bottom, and it's intentional. So you would have sort of your optimization problem. So think again about, you know, optimizing some transport infrastructure, or you can think about your favorite problem. And so this one remains, but there is, so we would call this the leader problem, right? So you're fixing your decisions, and then depending on your decisions, followers would react, right? And so the follower problem here would be that they have their own objectives. So let's think about people wanting to buy a certain flight, right? So the airlines want to maximize their revenue, so they're fixing prices. But when you're looking for your flight, you don't necessarily want to be aligned with that revenue maximization problem, right? You have your own objective where you sort of want to minimize the amount that you pay for your ticket. Maybe you have some preference with respect to sort of the comfort level you want to have. And so you have your own objective. And oftentimes, these are not aligned, right? You have your leader having some objective, and then you have your follower having their own. And when you have this sort of contrasting objectives, you can cast this, and sequential nature of the problem, you can cast it as a bi-level optimization problem. So this is sort of what we're doing here, and that this literature is doing. So now you have your combinatorial optimization problem on the top, and you will have a prediction model at the bottom, right? So what you want to do is you want to have your prediction there, kind of reflecting the preferences of the people. And when you're solving the bi-level optimization problems, you're still solving them jointly, right? You're not solving them sequentially. You have a solution process when you're solving them jointly. And there has been some work on this for transportation. Now I'm going into the transportation, but there is a lot of work on kind of game theory where you're using this. But for transportation, it's what is called network pricing, so mostly in revenue management. And something I've been working on relates to this park and ride example that I've been talking about all along, which is a competitive facility location problem. So you can think about it as a problem where you want to locate facilities in the network, so it's like an infrastructure. But if you have some other kind of problem on a graph that you're interested in solving, where you need to kind of make decisions on nodes in that graph. And then you want to, so you can think about the setting is that you have already facilities that are located, right? So the competition is sort of already there, and you want to enter a new facility or some new facilities. So you want to enter this market, and you want to add new infrastructure. Now, where are you going to locate that such that you're capturing as much demand as possible? This is sort of the setting of this problem. And I don't want to make it too technical. I said I'm not going to make a technical talk, but I needed some math here. Okay, so what I wanted to pinpoint here is that when we're moving into more sophisticated prediction models, the way these problems are solved typically is that they're using the specific structure of the prediction model. So you can think about a logistic regression, or what econometricians would call a logit model. Now, this one has a very specific structure that we can use when we want to solve the combinatorial optimization problem. It's super nice, and we can leverage their properties such that we can solve the problem effectively. Now, if we want to move to higher capacity models or anything else which doesn't have this nice structure, we need some other way of solving that problem. We cannot rely on the structure anymore. So sort of what we're proposing here is that you're looking at a generative perspective instead. So we're going for simulation. So we're saying, like, as long as I can simulate from this probability distribution, then I want to solve the problem. Now, the issue is that, so essentially what we can think about here is that I'm having my maximization problem. These are the parameters of my prediction model, and I have some other distribution here that also pertains to my prediction model. And so I want to now use sampling, so simulate from these so that I can approximate these expressions well. And this is the structure of this bi-level optimization problem that I was mentioning before. Now, the issue with simulation, and anyone working with reinforcement learning will know it a lot, is that in principle it works really well, but in practice you may need a very large number of simulations. And here we're integrating sort of all of those realizations when we want to solve a combinatorial optimization problem, which is already hard to begin with. So what we're suggesting is to say now, how are we going to simulate, and which of these scenarios that we're simulating are we going to keep such that we can keep our optimization problem still tractable. So we're sort of proposing a clustering heuristic that allows us to aggregate scenarios that are similar such that we don't impact the solution. And this is nice in optimization and also in reinforcement learning, is that sometimes you're not that interested in being super accurate at certain parts as long as they give you good decisions. So this is sort of the intuition of what we want to do here. And so essentially what you're doing here is that you have two important aspects, is that you have our cardinality of n here, and you can think of n as simulated customers or simulated users. And then you have the cardinality of s here, which is essentially simulations to approximate the probability distribution. So we have these two aspects that we need to simulate without going into the details of the maths. So what we're doing here is that we're looking at the uncertainty that we have in our model. So we kind of propose that you should not just look at a stochastic optimization problem without characterizing how much uncertainty we have. So we are giving a characterization and interpretability to our problem instances, which is characterized by its entropy. So we're looking at how much entropy do we have in our problem instances. And obviously, for a simulation approach, the higher the entropy, so the more uncertainty we have, the more scenarios we need. But this is good because we can upfront already decide, like, are we needing a lot of scenarios or we're not needing a lot of scenarios? And what we realize is that we can beat solution approaches. If the entropy is not too high, we can beat solution approaches, even those that are using the specific structure of the model. So we're just simulating, and we can still beat them, although you would expect that a simulation approach would not be a good thing, right? Because you need a lot of simulations. So we sort of show that that is not true, unless you have a super high entropy, so almost like uniform distributions. And that you will get if you have very poor prediction models, right? If your features don't matter at all and like your prediction model is more or less like a uniform distribution, then a simulation approach doesn't work very well. Otherwise, it can work super well. And what we also realize is for these type of problems, it's typically more important to simulate a large population. So if you think about this population being heterogeneous, what is important is that I draw a lot of individuals rather than perfectly kind of approximating the probability distribution that kind of, reflects how they're making choices. So this was on kind of part one, predict and optimize. I hope what you can retain from that is that it's challenging because you will have this, decision-dependent uncertainty. So you have like endogenous uncertainty in your optimization model. And when those optimization problems are NP hard, this becomes quite difficult to deal with. And there is still a lot of research to be done on that. Now I'm going to talk about decision awareness and why that is different from the standard practice, which essentially is predict and optimize. And I think you're going to recognize, if you've been working on this type of problems, what predict and optimize means. So I'm just splitting my box that I had earlier, right? So before I had like a blue box, predict and optimizing kind of going together. And now I'm separating. I'm going to say, like, I'm going to predict, I'm going to train my prediction models on some historical data, and I'm going to make it as good as possible. And then I'm going to use that prediction model for optimization. And I'm assuming that these do not interplay. You do not see any decisions now in my prediction model, right? These are completely separated, and I'm optimizing. This is how it's used to a large extent in practice. It's different from what I talked about in the beginning, because then you would have had your decisions in here. But even in this setting here, I would argue that it's super important for this prediction model to be decision aware, meaning that the only thing I really do care about is that these predictions lead to good decisions. And I'm going to try to convince you about why that is important. Now, before doing that, I just want to say, like, how do we usually train this guy here? We would use some sort of prediction criteria, right? So we would, you know, minimize some loss function. Here I'm just putting like a least square, sort of, right? But you can think about it being a least square or like a, you know, a maximum likelihood or whatever, right? So you have your loss, but what is important is that it's really some sort of distance between predicted and observed ground truth values. And so you're sort of forgetting about this blue guy here when you're doing that. This is all gray. Okay, so now I'm going to take an example of a supply optimization problem. So you're looking at the blue, that's our optimization problem. It's super simple. So I have two origin destination pairs, two ODs. Now, I didn't find any other. Eric was super good with his nice pictograms. I don't have so many nice here, so here's a bus, okay? But let's think about it as being like a capacity of 20. And it has a high fixed cost. So here I put a high fixed cost of 100. Let's assume that's a big high fixed cost, okay? And so now I'm having these two OD pairs. So I'm looking at my prediction and ground truth values for the demand of these two ODs. And I can see on my OD1 here, I have a ground truth value of 19, and I have a prediction of 21, okay? So it means that I could either be with 1 or 2, right? Because my capacity is 20, so if I absolutely need to satisfy demand, I would be sort of in between. So you can imagine that my prediction area is sort of like important here, right? It's like I'm at this, you know, change where either it will cost me 100, it will cost me 200. As opposed to the other OD, where the ground truth value is 9 and my prediction is 11. It's exactly the same error. It's 2 units of error, but here I don't really care, right? Because I could even predict, I could even predict that it's, you know, 12, 15, 16, 17. It doesn't really change anything for my decisions because I anyways need to put one bus, because here I'm assuming that, you know, but I think you get my point, is that I can have equal prediction errors but with very different decision costs, okay? Now, if I'm training my prediction models like here, they're totally unaware, right? They will always make the trade-offs in the training, trying to make as good predictions as possible, completely ignoring that some errors are not really important for the decision problem I want to solve, okay? And this is super important. So this is what is called decision awareness or end-to-end learning. So what you want to do is use what you could do, and I'm going to say what you want to do because this is sort of like quite new research area, but what you could do is using some sort of regret minimization instead. So what you're seeing here now is that I'm telling, when I'm training this prediction model, I'm telling it I actually have decisions, right? And so I have some objective function here, and this is the guy that I really care about. So this is my G, and now I have a regret, which compares my ground truth values to my predicted value. But what I'm comparing is actually objective function value, right? So here I have my objective function value if I solve my optimization problem using my prediction. And here I have my objective function value if I solve my optimization problem using the ground truth value. And now suddenly I have this sort of decision awareness. Now, any one of you who have been training machine learning models will tell me, well, you know, okay, so I want to evaluate this, then I need to solve this, right? So if I want to use some sort of, you know, descent direction here, I would need to differentiate through this argument operator here. And that's not trivial. And so this is sort of the challenge here. And what is interesting is that if this problem here is a linear program, so you have only continuous decision variables and sort of linear constraints, then you can actually effectively differentiate through this argument operator. And so you can sort of use that fact. But when this optimization problem is a discrete optimization problem, which we're interested in for transportation and mobility, but also a bunch of other optimization problems and applications, then that's not true anymore. It's quite difficult to differentiate through this, and it's very costly, and it's sort of unclear how to do this in a good way. So there is some literature on this, but this is an exciting problem, and it turns out that this is really important, and I'm going to show you an example of the why this is high value in practice. So kind of an open question right now, which is another topic that you might want to kind of start working on, is how do you get decision awareness, or how do you kind of get good predictions and integrate this when the optimization problem you're interested in is like a mixed integer linear program, or more generally discrete optimization problems where you have predictions not only on the objective function but also in the constraints. So if your predictions are sort of also defining your feasible space, then this becomes quite hard. But there is some literature, so I will flash all the references at the end. But there is some recent literature on this topic, but I would say that it's to a large extent the open question. There are related topics for those of you who are working on reinforcement learning. It's quite new, like decision-aware model learning. Well, it's been around for a little while, but it's still kind of at early stages as well. Then instead of having kind of mathematical programs as the optimization problem, you would formulate them as market decision processes. And it's somewhat related also to inverse problems. So let's assume I was saying that we're really interested in the objective function value here, and that we only have like these ground truth values for the predictions. But let's say that we also have access to our solutions, the Z. And so for transportation and mobility, I was telling you like we have these recurrent problems often. So often we do have the solutions. And then to me, this is sort of, related to inverse optimization, because I would have my ground truth values and I would have my Z's. And so there is starting to be more, but it's also a fresh research area on data-driven inverse optimization with noisy data. A lot of the inverse optimization literature I've been interested in linear programs, not noisy data. So from a machine learning perspective, that is like perhaps a no-go, but they have some nice properties of the problems. But there is starting to be like more, problems that are interesting from a more practical point of view there. And there is also the literature on inverse reinforcement learning. That started in 2000, but there is like a surge of literature in that, and which in turn relates a bit to dynamic discrete choice models in econometrics. So I just wanted to talk about related topics to this. So I've been sort of saying, like, why am I talking about this in an applied machine learning conference, right? You're interested in solving real-world problems, and here I've been just saying, like, what are the problems we can't solve in research? Because for me, we're really don't having problems, like approaches that scales to sort of the large-scale problems and the messy problems that occur in practice. So I'm working a lot with the Canadian National Railway, which is one of the largest railroaders in North America. And they have really tough, as do, European railroads, or railways, we say in Europe, these combinatorial optimization problems that are really hard. And so we sort of wanted to get this decision awareness, but we know we can't solve it as a real, decision awareness problem. So I'm going to quickly talk about this problem, so I have a few minutes to talk about the last topic as well. So I'm going to introduce, when we were working on this, we needed to introduce sort of a new problem to put attention to this decision awareness problem. So think about that you have a tactical planning problem which is cyclic. So you can think about this as train scheduling or like service network design. So you need to kind of show you have a schedule that repeats, or like you have services that repeat over time in each period. So I'm giving an example here. Let's say, so this is the network of CN, the Canadian National, so you can see it's quite big. And they want to have, so that their customers can adjust, they want to have, always on Mondays, Wednesdays, and Fridays, they have a departure from Montreal to Toronto with certain capacity, another to Vancouver with a certain capacity, and so forth. So they'll repeat such that their customers, in their turn, can make plans, right? So these plans typically repeat over a season. Let's say they have a summer schedule or whatever. I know in Switzerland, your train schedules don't change very often, I think, but they do, I mean, make some major adjustments from one season to the next. And then every week you have a sort of operational plan, which might be a bit more hidden. Like say, you don't change necessarily departures, but we can see here is that I changed the capacity, right? So I have Toronto, I still have a Toronto departure, but I realize that I have a bit more demand. So I'm sort of adjusting my capacities on a more daily or weekly basis without necessarily completely changing my service network design. And I can even put in some extra trains, saying like, I have so much demand I didn't anticipate, so I'm going to put in an extra service and I'm going to run that. Now, what is important, if I want to, now my focus is going to be on this cyclic plan here. So what I need is essentially a good estimate of demand that it's going to repeat in each week, right? Because I want the schedule to repeat. So I want to have an estimate of more or less like the most likely demand. And when I'm talking about demand, I'm talking about how much to transport between each of the origin-destination pairs between, you know, every day of the week, more or less. So this is sort of a large-scale problem. I will call those commodities, and often we have, you know, hundreds of commodities that we need to predict. But when I'm using data, this is not the data that I have necessarily, because data come in on a daily basis. It's like, how much did you transport? Right? Day by day, so I have like a time series. But then I want to transform that time series into this sort of repetitive demand. And then you can say, okay, but that's a distribution, right? So I have, you know, let's think of it as I have a time series, a multidimensional one of like, say, hundreds of time series. And I know that I want to have some sort of what is going to repeat, so I can construct some sort of distribution. But then I go into a stochastic optimization problem, which at this size I cannot solve. So now we're in practice, we need to be pragmatic. So in order for me to solve this tactical planning problem, I need a deterministic formulation. I need to have a demand for each commodity in each time period. So how am I now going to transform these time series predictions into this repetitive demand? And what I want to do is I want to do that in a way that is decision aware. Right? I want to do this mapping because I know that I only need to do that such that my decisions are good. This is the only thing, right? And this is an illustrative example why this matters. So you can see here on the x-axis you have time. Each dot is a demand. So here you sort of have your time series. On the y-axis, so you have the amount of demand. What you can see here, there are two very different distributions. If I'm looking at the mean here, which is the solid line, they are identical. But if I look at any other moment of this distribution, they're different, because we see that the distributions are very different. And what is done in practice is typically for these kind of repetitive problems is just to say, oh, so I'm having a time series forecast, so I'm going to take the mean, and this is going to be what I'm going to plan with, right? I need one value, take the mean, makes sense, right? Now, what we're going to show is that it doesn't make sense. You should not use the mean. You should look at what matters for the decision-making problem and then do a mapping from this time series to a value that sort of take into account the trade-off. So remember my bus example, right? You want to make sure that you're kind of hinging against uncertainty where you will flip services, so you will incur a high fixed cost. Right? We saw that with just a small error, I could flip between having one bus or two buses. And this is exactly what happens here, is that you just don't want to use simply averages. What you want to do is that you want to look at the decision costs when you're making this problem. So essentially what we're putting forward here, and for the sake of time, I'm not going to go into too much detail, is that so you're having a demand forecasting problem, which essentially is time series. Usually you would just, skip this orange box here. You would do your service network design problem, and then in the operations, you would adjust that plan. Okay, so what we're proposing in this work is that we say, look at these two boxes here. They represent the costs that are really interesting to me, right? So I'm feeding forecasts, so I'm still in a predict, then optimize setting, because I can't do like this fancy regret learning in this for these large-scale problems, right? This is why I need you guys to work on this problem. But what I can do is that I can still say I'm going to take into account the cost that I incur here when I'm deciding what to do with this guy here. What am I going to feed as predictions? So what I'm going to do is I'm going to formulate another optimization problem, okay? Which says that find me a mapping from time series forecast to a periodic demand, right? Find me that mapping such that I hinge against high costs here, okay? So this is what I'm going to do, and then there are some challenges related to actually our historical data is censored, so we're having truncated data and so forth, but I'm not going into the technical details. That's what we're doing. So we're formulating another optimization problem, essentially, that is easier to solve, that is easier than doing training that is kind of decision aware, but we can still get, you know, this decision awareness to some extent, right? So now we're being pragmatic. We want to solve a real world problem. That's why I wanted to talk about it here. And what we're doing is that we're doing it in an interpretable way. So essentially what we're saying is that what people are doing in practice is to use the mean, right? So you have this Y here, which is prediction for commodities. The P is for periodic. So I have one for my whole kind of season per commodity, which is weekly. Now I'm saying like this mean may not be such a good idea. So I'm going to multiply this element-wise with a vector, which I'm calling like deviation coefficients. So it's telling me like how far should I be from the mean such that I'm hedging against this uncertainty that I was mentioning, reducing costs. So now suddenly I have something that is nice and interpretable that I can tell, you know, my industrial partner to say, you know, you would use the mean, but I'm telling you to use differently, and this is why, because you're really sensitive to high costs on these specific ODs. And so what I'm showing here is sort of a case study. And so on the x-axis here, I'm having 170 commodities. Okay, so I have a time series for each of these commodities. And I'm clustering these according to these alphas, right, these deviation coefficients. And here you have the value of these alphas. And I have a red bar here, which corresponds to the average, or the mean, okay, the arithmetic mean of all of these. So if you were to use the state of practice, it would mean just using the mean. And I'm telling you not to do that, because on certain ODs, you really need, you're sensitive to high values of demand. And this is what it tells me. So for these commodities here, or actually for a lot of them, this coefficient is greater than 1, which means that if you want to minimize cost, you should choose a higher one. So you could choose sort of like the third quartile or whatever. Here we're solving the problem, so we know exactly what to use. But we cannot solve this for the size of the problem. 170 still results in a too large optimization problem to solve. So we're doing a clustering, and that's why they have equal values here. So we have sort of a clustering approach to do this. And what we realize is when we're solving real instances here is that it leads to really big cost reductions. So 15% here is sort of a conservative estimate compared to some of the problem instances that we solve. So this is essentially the value of decision awareness. So if you really, even if you're in a predict then optimize context, and you have a problem you can't do, or there is no state of the art to actually introducing this in the learning, you can still sort of, you know, make sure that you take into account this decision awareness to some extent, and it can still lead to important cost savings. And finally, I think I have maybe 5 minutes, do I have? Or?
You still have 15.
Oh, okay. Okay, I want to leave some time for questions in case they have. Okay. So my third part, it's the last one, and it's about measuring impact. And so now you can see that we're having like the predict and optimize, the decide, and then interact. So what I'm going to be interested in here is to assess what is the impact that I'm having in reality when I'm working on the prediction and optimization side. And so this is something I was involved in working as a scientific advisor for Ivado Labs with Air Canada an airline. And it is on arXiv, this paper. And so what I'm going to advocate for is that assessing the impact can be cast as a counterfactual prediction problem. Okay. So now let's say that we have been working on this, blue problem here. This is what I've been talking about for a long time. Okay, now if I'm assessing the value, and even in the previous work I said, oh, this leads to 15% cost reduction, okay? What I'm doing essentially is saying, like, my models here are true, right? This is an accurate kind of representation of the actual cost and so forth. And then I'm comparing the cost between solving the problems in different ways. And then I say, according to this objective that I have here, I have cost savings. That is what you're going to see in almost any scientific paper. I would say, like, a huge amount of the scientific literature, you would have that. If you're in RL and you're doing, you would say, like, okay, I have some digital twin, or I'm having a simulation environment. And according to that simulation environment, I'm getting this cost saving. Now, we all know that this is not true, right? Our models may be super good, but they are not that good, right? Because there are a lot of things that can happen when you're actually executing these solutions in reality that don't go as what you were anticipating when you were simulating. So what you're actually interested in doing is not looking at this guy, it's like looking at what happens when you're actually implementing things in reality. Right? That's the actual value. So if I'm working on this, I'm making some sort of improvements, what I'm interested in saying, like, if a company asks you, like, oh, should I invest in this? Right? You're building a super fancy solution. You're saying, okay, putting my AI model in production environment will maybe cost you, I don't know, $500,000 Swiss francs. Okay, so now, is it worth that $500,000 Swiss francs or not? And so that means that you want to, either you're betting or you're very trustworthy, or people will tell you, well, do me proof of concept, right? So implement it, in some limited trial, maybe not pushing it completely to production, and measure the actual value. So what we want to do is that then we want to run this test, or the proof of concept, and we want to compare the value that we get to some sort of business as usual. Right? This is what you're interested in. Now, this is the tricky part, because you want to then compare it to what it would have been if you did not do that proof of concept. Right? So think about, and this is the example that I'm going to take, so think about an origin-destination pair kind of setting. I'm going to talk about an airline setting. Right? So let's say I'm impacting the pricing on a certain number of flights, or origin-destination pairs. Geneva, Montreal, some other ODs. And I'm running a proof of concept of those. So the prices are changing because I'm playing around with this blue box here. Now, the value for those is the value that I'm comparing with is the value or the revenue that would have generated if I did not play with this blue box. Because I still want to have these two values to compare. Right? I'm going to show the example earlier. So my case study here, or the use case, is that I'm improving the prediction models. So this is Air Canada. They had like kind of a legacy system. So they have the revenue management system, and they were saying, we can't touch the complete revenue management system. I mean, you just can't go in and just say, I'm going to redo a part of your, a revenue management system like that. So you're saying, like, we know our forecaster is not accurate. And so we're having a team of demand analysts that are working with sort of adjusting those forecasts because they have information their prediction models don't have. But then you go into COVID period or wherever, and these demand analysts suddenly become the forecaster because the forecaster is completely off. The data is completely, out of their training distributions, and you need to do something. So what we were doing is that we were giving them another forecaster. So you can sort of think about the demand analyst looking at the revenue management system, and then they're getting an additional forecaster with an interface telling them these are how different the two forecasts are. And you should really go and do something about these ODs or like these departures because they are really not coinciding and you should trust us. Essentially, that's what we were telling them. Okay. Now, what we're interested in, so when we are changing these predictions with the human in the loop, They are still optimizing the prices as before, so we cannot measure what is the value of this guy without actually measuring the actual revenue in practice, right? So what we're going to do is that we can act on this here, but we're going to measure the actual impact in reality on revenue. And so we were giving a user interface to the demand analyst, and without going into the details, this is essentially like a heat map just showing like a view that is easy to digest, that sort of looks at the distances between all of the forecasts. So you have thousands of forecasts here, right? So you cannot tell a human, like, go and look at each of these thousands of forecasts. Instead, you're telling them, like, these are the ones that you should pay the most attention to, and we think that you should, you know, increase the forecast by a factor of 1.4 or whatever on these ODs. So this is essentially what the user interface tells them. And so what we wanted to do was to assess the impact. So essentially what you can think about is that here on the y-axis you're having revenue, on the x-axis you're having time. You have like business as usual, which is pre-test. So you have a time series per origin destination pair here. So essentially representing the revenue that you're capturing for each of the ODs. Now let's look at this red OD here. Is the one that we're going to impact. So it's just an example here, right? So I'm observing the revenue of this OD, and then comes the test period, which we'll call a treatment. So we start the treatment, so we're changing the predictions. They're using our tool. What we hope for, obviously, is that the revenue will increase, right? But now the revenue will increase. So this thing we will observe, right? The one we will observe, because this is the revenue under treatment. We're acting on this one. But the line that it would have been business as usual, suddenly now it's unobserved. I don't know it anymore, right? Because this is what it would have been if we were doing business as usual. And the difference I'm interested in, the impact, is the difference between these two, right? And actually, I'm interested in the area between these curves here, because over the trial period, I'm interested in kind of the total revenue that we're generating more. Now, what is particular to this setting is that we have a lot of ODs, right? So here, if we look at all, we have 3,000 or we have more, and we're only going to impact a few of these. Now, we're going to cast this as a counterfactual prediction. So this guy here, we will try to predict. And the reason why we want to do that is we want to measure actual impact. So we don't want to do simulation. And this is what sometimes is done. You're simulating, but then you're assuming your models is true. So we don't want to do that. Otherwise, in practice, often you would use like a year-over-year different change, or like do some A/B testing. But both of these sort of rely on the fact that you have ODs that are actually comparable and that they're not too noisy. But actually, we were trying to do that, badly trying to do that, because we were thinking that it would be a lot easier. The issue is that there are like no matching ODs. Like you cannot do that, because what you want to test, if you have an uplift of say 2% of revenue, that's great. Okay? But measuring a 2% improvement, that's still relatively small. I mean, it can be very large when you run this system over a long time. 2% of revenue is like sometimes the best you can hope for when you're impacting this system. But measuring in terms of statistical significance, a 2% increase, over limited duration of time, that can be very hard. So when you're doing this kind of simple year-over-year or A/B testing, it's simply too noisy to be able to say something with statistical significance. So that's why we're sort of resorting to counterfactual prediction. And what is interesting, and this is sort of, I invite you to go there if you're not using this, they've been developed a lot for more like macroscopic questions. So looking at, say, the impact of the German reunification, right? So you're having, these kind of big macroscopic questions, and you want to do counterfactual prediction. And here I'm just giving a few examples of those models. But what is interesting is that you can also use it for microscopic applications. And what is specific here is that whereas in macroscopic the impact can be high, here often the relative impact of the tools we're kind of developing, we would hope for improvements of 15%, but in reality, I mean, 15%, I think you're all aware, that's like huge, right? So you're looking in relatively small impacts, But you have a lot of controls, right? Unlike microscopy, if I'm looking at countries, maybe I can try to look to have maybe 5 countries that are similar. I can use the controls. But if I'm in transportation and mobility setting, and for me they were OD pairs, suddenly I have a ton of them, right? Which means that we can explore that fact. And so what we find here is that we get quite accurate results. So we were trying to, using 30 OD pairs here, which is really small compared to the overall network. We carefully chose, like here was a bit more than 300 controls that were kind of helping us for the counterfactual prediction. And what we paid particular, what needs to be careful with is that there should be no interference between these, right? So you just want to make sure that you're choosing control ODs that will be completely unimpacted by whatever proof of concept you're running. And what we realized is when we were running, we wanted to see how accurate we were. We were running a simulation study, and we think that we can actually, detect with statistical significance quite small improvements, so 2% and above, and our prediction errors were actually less than 1%, and this is on real data. So in conclusion, predictions are often, used to make decisions, in particular for transportation and mobility, but I can think of a ton of other applications. And in that context, it's important to integrate further, and I think this is, there is research going into this, but definitely need more research. And we also need to, find ways also for practical applications to try to make this integration stronger, because there is a high value associated with connecting these problems. Now, it's challenging, in particular when our optimization problems are discrete optimization problems or combinatorial optimization problems, because it leads to what we would call endogenous uncertainty, and this is hard to deal with. And it should impact not only how we're solving our optimization problems, but also how we're training prediction algorithms. And that was what I was trying to push for, this decision awareness in learning. And I think something also that is important that we tend to forget, at least in research, I know in practice you don't forget that, always eyes on the price, on the actual value, but I think that we should be better at trying to look at how will this actually work in a real setting, right? When you're integrating with a real environment, and the data that you get back, if you're in a recurrent setting, is sort of noisy and can move you away from whatever were your training distributions before. And there are other issues I didn't have time to talk about, but I think there are a lot of research and practical work that could go into addressing these open questions, which are open on both sides. So this was all I wanted to say. I would be happy to take questions, and I was sort of flashing all the references. Thank you.
Thank you. Thank you, Emma, for this inspiring talk, especially also for us from the industry to see all the way from academic research to the challenges when trying to implement it for a company and taking pragmatic solutions. I've seen lots of your work and always inspired, so it was a lot of fun listening. I could have listened for a few more hours. But we have some time for questions before we go to the next speaker.
Thank you very much for the great talk. I have a bit more of an academic question. So if you're integrating prediction into optimization, so if you have it separate, prediction and optimization, it's like trying to understand the market, try to take the best action given the market. If you're now starting to integrate this or say decision dependence into your optimization problem, aren't you adding a new component, this like market shaping type of approach to your optimization problem? So you now try to find the best solution given your ability to kind of impact demand. Isn't that leading to like different solution concepts?
Yes, it does. And so one way, what I was trying to show, so I'll go back a bit. So the way we did it in the first work here, so I tried to so you're changing your solution space when you're doing that, because essentially what you want to do is that you want to optimize your decision anticipating, right, what would be. So this anticipation becomes because you have this connection between the prediction and the decisions. And so this is what makes them inherently difficult, and also why the solution space change. When you think about it, is that if that is the actual world, then it means that your solution space that you're up is actually different from the one that you would have if you're ignoring that concept. But the way we did it in this work was that we were really casting it as a bi-level optimization problem, which really, like to your point, it really changes, you know, your solution space, because now you're having this hierarchical optimization problem instead of just, you know, your often like deterministic problem ignoring this feedback that you would have from the users. So you're totally right. Yeah.
Okay. Yeah, just to give you a bit more context, because I'm a bit concerned. I'm more coming from the ML background. So you have similar scenarios also in, say, recommender systems where you have preference shaping. And there, this component of steering is a bit different to just anticipating, because you can really instrumentalize it. It's not about only being better, but also about like changing the world that you try to predict.
Yeah.
So that's probably a bit different in this context, but I just wondered whether you've looked into these questions or whether that's...
Yeah, so one of the questions I did not talk about at all, which is important from the perspective that we hear. So, I mean, what you're referring to is often what is tried to be achieved in demand managers, so management, like pricing problems, right? Because actually your intent is actually to impact the behavior and maybe change the behavior, right? Such that it is, you know, to some extent in your favor. You're trying to shape. Sometimes it's to make better use of the capacity, sometimes it's to maximize revenue or whatever, but I think there are synergies to your point. Now, what is another line of research which is really important here is that when you're doing that, you're intentionally getting, if you want to change, you're intentionally going out of distribution. So your prediction models would probably be wrong, because whatever you use to training, and I think this is similar to the issues that you're having, that you're referring to, right? That you're actually need to have good out of distribution generalization, which is really hard. And some work is now going into like what we should know here is the causal structure between the decision variables and the predictions, rather than kind of, you know, a purely statistical model. So there is work going if your point is sort of like issues related to outer distribution generalization, but for sure this is something that we're having here too.
Cool, thank you very much.
Thank you. And I think we would have place for a short question if somebody likes, or we can move on.
There is one, Erik.
Ah, sorry.
I'm just a little bit concerned about how, if you have any suggestion or advice on how we can make assumptions in simulation more realistic. What should I care? And yeah, that's it. Thank you.
Yeah, the million-dollar question. I don't know. I'm just remotely familiar. Like in robotics, you're really interested with this, and like the sim to real kind of issue. I think we're all facing somewhat similar issues. I don't have a good sort of answer to that, other than trying to. I mean, I was talking about assessing sort of the impact when you go here. I think that what we should be better at is sort of having more information of, you know, enhancing our understanding of the systems when you're doing, you know, when you're interacting. So sort of doing this jointly. I know there has been, I mean, a lot of work in sort of optimal control and system identification going in there, but not necessarily on the simulator side. I mean, this very hard question. I think, yeah. I don't have a good answer. More than, so most of the research I'm aware of, and a chunk of the literature sort of just choose to ignore it, unless there is like a specific topic like sim to real or whatever. But otherwise, you're kind of saying, I need my results, I need to have something to compare to, so I'm assuming my simulation model is more or less accurate. But I think we should pay more attention to that. I think it's hard to publish, and it's very expensive to run those kind of experiments, so I think that's maybe one of the reasons why there's not so much research on it. But super important concern. I don't have a good answer.
If somebody has a good answer, we would also be interested in that answer. So that's good. So let's thank Emma again for this great speech.